back here looking at another video focusing on the application of vectors. So you may have previously looked at projectile motion. I'll put a little link here if you have yet to look at that. That's one way we can look at vectors and how they can be applied. So here in this video we're focusing on this concept of work. And it's, in general, you're applying a force on an object over a distance, and here's the more formal definition. So some examples I can tell you is, imagine you're pulling a box along the ground. That is an example of work being done. Pushing a chair across the floor, you are applying work to the chair. So anytime you pull or push something over a distance, or you carry something up, you pick something up, you are actually performing work on the object. Now, the units, because with force, we have pounds, we have newtons, and then for distances, we have feet, and we have meters. We have two different units possible, depending on how everything's measured. So the most common way of measuring work is what's called a Newton meter. Newton times meter. But it takes up its own name. So we, rather than say a Newton meter, we say joules. Joules of work. And then alternatively, we have a foot pound. I know it's minus, but it's just a dash. So we have foot pound as well. So two different types of units for work. Now, how do you find work? I said here it's force applied over a distance. How do you actually calculate that? So there's a couple formulas here, and it all depends on what we have. The first formula is, so the work being done can be found by multiplying the force by the distance traveled, the distance that the object is displaced. Now I want to say this seems like a very simple formula, force multiplied by distance. Well, this is good only if the force that's applied is parallel to the displacement. D here represents displacement, okay? So we can do that. So F parallel, so this is where the force is applied. Force is applied parallel to the direction of motion or displacement. Okay, that's the most basic way of calculating force, but again, it doesn't happen every time. So what if the force is not parallel to the direction of motion? Okay, so imagine you're pulling a box with a string. You're not going to pull the string close to the ground. You're going to be pulling the string closer towards your waist. So if the force is not parallel, we have this version. So the magnitude of the force multiplied by the magnitude of the distance vector, typically you're just know the distance, and then multiplied by the cosine of the angle in which the force is being applied. So this angle, so this theta, is the angle between the applied force and displacement. We'll have an example of that. All right. So you're going to see this formula rearranged a little bit from now when we actually look at the problem. But this is force times distance times cosine of the angle. So now, what if you don't know the angle between the two vectors? Okay, so what if we don't know this angle? So we have our last version of work, this formula. This is the force vector. Okay, so we're going to have a vertical component and a horizontal component. So we're going to take that and perform the dot product on the displacement vector. So displacement vector, we could have two components there. We could have maybe a vertical component and maybe a horizontal component. But we're going to have vectors that will perform the dot product on. And even the displacement, it could have a zero component. So I'm going to say this here, that this force vector will be the magnitude of the force, often given to us, multiplied by the cosine of theta, comma, the magnitude of the force, multiplied by sine of theta. So that will be the force vector, and this D is the direction vector. Okay, now I'm going to write this. Because finding this theta is not going to be the same theta as here. Because of this theta, it's often going to be cumbersome and time consuming to find this theta. We can, as an alternative as finding theta, we could take the magnitude of this force vector, again, it will be given to us, and multiply it by the unit vector of the desired direction. Again, this will make more sense once we look at an example. So I just wanted to have you have this here. So 3 different formulas, all depending on what we have. So let's take a look at some examples. So let's say we have, okay, not this one. I don't want to do that one first. I want to do this problem first. Okay. So find the work done by lifting a 100-pound bag of potatoes 3 feet off the ground. All right, so we are taking a bag of potatoes and lifting it up. So in this, notice you're not given an angle measure. This pound bag, that's actually the force that we're going to be using. And we have the displacement 3 feet. So this is just straight out. The work done is force multiplied by the displacement. Okay, so 100 pounds times the 3 feet. So that's going to be a work of 300 foot-pounds of work, or pounds-feet, however you want to write that. And there you go. Because the force is applied parallel to how the bag's moving, okay? If the bag's moving up vertically, but I'm applying the force like in a different direction other than up, then I'll be using a different formula. Just understand that. Parallel force to displacement is just that simple. So let's look at another. So calculate the work done by pulling a box 8 meters across the floor. So here's our D. Using a string that is 42 degrees with the horizontal. Okay, so we have our theta. The box is pulled with a 12.3 Newton force. There's our F. So we have our force magnitude, we have our displacement, we have our theta. This is exactly force times distance times cosine of theta. Okay. And let's see. So we have force, we have 12.3, we have displacement 8, and we have cosine of 42. And with our calculating device, let's see what we get here. Yes, all this work can be very tiring. Ha, ha, ha. So we have 12.3 multiplied by 8 multiplied by cosine of 42, and we get a work of, oh, look at that, guys. So eager to get this done, I did not change its radians, or from radians to degrees. Okay. 12.8 times 8 times cosine of 42. 73.1255 joules. Joules because we are dealing with newtons and meters. All right. So I'm gonna take a quick moment here. So just give you a visual. So we have a box. Okay. We have a string on a box, and that string is being pulled at 12.3 newtons with an angle measure of 42 degrees. So we have learned how we can take that magnitude with this angle measure and look at the components, right? we have. So this force times cosine, if I place the cosine up front with the force, that would actually be this value. Can see it? There we go. That would be this value. So we just changed the formula from above. So we now have the parallel force cosine theta, multiplied by distance. Okay? So let's see what we have next. So the angle between a 200-pound force and a direction of AB, 2I plus 3I is 30 degrees. Find the work done by the force in moving an object from A to B. Okay. Now understanding this, is what's new here is this. You're thinking, oh, this has been really easy now. Now we have a problem like this. So we have a 200-pound force. So right here is our magnitude of the force. We have a direction. We have theta. So what do we not have? Well, if you think about it, we do not know how much it's been moved. So we have this vector. Find the work done by the force in moving an object from A to B. So if I knew exactly maybe the length of this vector, then I would have my displacement. So we're going to say D here is really the magnitude of A to B. Okay, so that's the square root of 2 squared plus 3 squared. That's 9 and 4, so that's square root of 13. Perfect. So that's square root of 13. Then that means for us that the work is magnitude of the force times the distance times cosine of theta. Okay, so that would be 200 multiplied by the square root of 13 multiplied by cosine of 30, which is approximately 624.49998. And looking at our units, we're pounds and so pounds. So we're looking at foot-pounds. Okay. So we looked at what was given. Notice that we were not given displacement, but the vector given knowing the magnitude is our displacement, and we had exactly what we needed. Let's try one more, guys. So what if we're finding the work done by a force of 30 newtons? So again, great, we have our force magnitude, okay, acting in the direction of 4, 5, okay, is moving an object 5 meters. That's convenient. So we have 5 meters. That is our displacement. Perfect. So let's think for a moment. So we've been using force, magnitude of the force multiplied the magnitude of the displacement multiplied by cosine of theta. Theta being the angle of the force from the displacement. We don't have that. We do not know this theta. So what we can use here is actually the last version of our force, of our work formula, where we take the force vector and perform the dot product on the displacement vector. Okay? So how are we going to do that? So force vector, we had said, can be found by taking the magnitude of the force, multiplying it by the unit vector of the direction you desire. So we desire to go in this direction. So we need to know the magnitude, the unit vector given this 4, 5. So let's think. Unit vector, imagine this is V. Okay. Unit vector, we take the unit vector and divide it by its magnitude. Well, the magnitude of V would be 4 squared and 5 squared, so that's 16 and 25, which is 41. Okay, so then the unit vector is 4 over root 41 and 5 over root 41. That's the unit vector. So the force vector is going to be the magnitude of the force we have, which was 30, and multiplying that by the unit vector we just had. Okay? So distributing 30, that gives us 120 over root 41, comma, 150 over root 41. Okay, now what do we got? Oh, our displacement vector. Well, we were moving an object 5 meters. We're told from 0, 0 to 5, 0. So we've learned how to do this. X2 minus x1, y2 minus y1. Our force vector is going to be 5, comma, 0. We're just going to write 5. All right, let's perform the dot product now. We have our two vectors. Let's go. So we have, all right, 120 over root 41, comma, 150 over root 41. Dot product with 5, comma, 0, which would give us, oh, dot product, x component, y component, y component. So that would be, let's see, 120 over root 41 times 5 plus 150 over root 41 times 0. Oh, that's nice. That whole entire piece is going to go away, which would give us 5 multiplied by this, which is approximately 93.7043. And looking at our units, we're in meters, newtons, joules. All right, so this is probably the max. This is rather complex, knowing that we needed to find two vectors because we did not know the angle measure. Okay, found the unit vector, multiply unit vector by the magnitude of the force, and yes. All right, guys. So you're gonna be practicing this. 3 different formulas, 3 different ways of finding work, depending on what we have. So I wish you the best of luck here, practicing each of these variations. And guys, I'll see you in the next video.